Okay, welcome back everyone. So let me give a two-line summary of this mini course up to date. The first thing was to define a topological space, and it was basically a set S and a topology U, and that a topology is the same as collection of open sets. It's not that if they were open sets, they were in the topology. Rather, if they are in the collection U, then we call them open sets. So that defines a topological space, subject to some conditions, which I'm not writing down. Now, the second was differentiable manifold. And this one is a topological space together with an atlas. Okay, and the atlas had to have the property that on overlaps, it was the charts were C infinity compatible. Charts so atlas requires that charts be, well, let's see how exactly. Let me go back to the definition of atlas. I think I introduced compatibility a little later. It's just yeah, no, it's there. So charts compatible on overlap. Okay, and now equivalence of topological space. So topological spaces came up with a concept of equivalence among them, which was called homeomorphism. And today we will discuss equivalence between differentiable manifolds, and it will be called diffeomorphism. But first, I need to define a few things, so give me a minute. So this is a summary of where we are now. Okay, now I need to define some things, and the first thing I need to define is the following. Supposing I have two manifolds. So two manifolds. If I just say manifold, I mean differentiable manifold, X and Y. And I have a map, a function from X to Y. This is a new situation. If you remember, last time I had one topological space and I made it into a manifold by introducing charts. Now I have two topological spaces which have already been made into manifolds by introducing an atlas. Okay, and I have a function between them. Now, this is very important. This is actually the crucial point why we did all this definition of manifolds. So let's draw it. This is the space X, and the function f takes every point in X to a point in Y. Okay. Now, supposing I look at, okay, not just, it doesn't, yeah, okay, sorry. Now, supposing I look at an open set U in the X, in this first X, and another open set V in Y. So what do I know about U? Because X is a differentiable manifold, I know that there's a homeomorphism called phi, which takes it to a piece of some Rn, and that piece is called phi of U. It's just the image of U under phi. And phi is a homeomorphism, and that's very important because then it's continuous in both directions and I can follow it in either direction as I want. Now, same is true for Y. It has its own homeomorphism, which I'm calling psi, just to give it a different name from phi. And it takes a any particular open set V in Y into psi of V, which is some open set in Rn. Now, actually, this one I'll put in Rm because I'm not assuming that X and Y are manifolds of the same dimension. They could have different dimension because now I'm considering a map from a manifold to a manifold. So far, I've never considered that. Okay, good. So here is the situation. Now, the thing to note is that this setup defines a function between this set phi of u and this set psi of v, and this function has a complicated name. It's phi inverse composed with f composed with psi. Sorry, all wrong, other way around. It is phi inverse composed with f composed with psi, from right to left. You can see why it is so, because this, I claim this is a function which takes me from here to here. Okay, and why does it do it? Well, first I act with phi inverse, that takes me by definition from here to there. Next I act with f, that takes me from here to here. Okay, and next I act with psi, and that takes me from here to here. So all in all, by doing this process, I've actually defined a function which goes from phi of u to psi of v. Okay, good. Now, very good. Now, the key point here is that in this process, we've reduced the original function f to a new function. The original function was between two manifolds. The new function is between Rn to Rm. What's the difference? Well, when it's from Rn to Rm, we know how to do anything we want with it. We can do calculus. But this function, f from x to y, we didn't know how to do anything. So whatever we want to do with f, we'll do it with psi f phi inverse. Actually, we'll be very careless sometimes. And this whole function, we will sometimes call it f. It's a kind of typical abuse of notation which physicists do, but even mathematicians do sometimes. We'll just call this f because it contains the same information as the original function, assuming that x and y already come with their given homeomorphisms, namely their given charts. So they already come with all that. So essential information of the original f is captured by psi f phi inverse. Okay. Now the key idea is that I can ask whether this function psi f phi inverse is differentiable or not, because it's a function from Rn to Rm and this is calculus and I can differentiate it. Okay. So here's a definition, natural definition. If there exists now, there's an extra thing. Okay, so there are two different definitions and slightly I'm mixing them up. So I want to write it properly. So let me give you, it's slightly different from how it's done in the book. Okay. We will say that the function f from x to y is differentiable if the function, I should have written it this way in the book, the function psi composed with, so phi inverse composed with f composed with psi from Rn to Rm is differentiable in the usual sense. So just to repeat, sorry if I repeat too often, there's no usual sense to differentiate the original function f of x from x to y, because x and y are topological spaces and they are differentiable manifolds, but we don't have any formalism to differentiate a function from a differentiable manifold to another manifold. What we do instead is use the manifold property to take that function to a function, this one, from Rn to Rm, and we differentiate that. So if it's differentiable, we just call the original function differentiable. There's no theorem involved here. It's a definition of differentiability of this function using the known concept of differentiability of this function. Okay. I hope that's clear. You can keep putting your questions in the chat box. I'll come to them eventually. Okay. So now I have the interesting definition that two manifolds x and y are said to be diffeomorphic if there exists f, a function f from x to y, such that, first of all, acting as thought of as topological spaces, x and y are topological spaces, f is a homeomorphism. Secondly, f and f inverse are C infinity, which means infinitely often differentiable. And here I use this definition of differentiability, namely that these functions f from x to y are differentiable if the phi inverse f psi, that function from Rn to Rm, is differentiable. Okay, so if two manifolds are first of all homeomorphic as topological spaces, and then there exists this function, which the function we can call it a diffeomorphism satisfying these properties, then the two manifolds are called diffeomorphic, and we say there is a diffeomorphism between them, and we treat them as equivalent. So it's an equivalence relation. Okay, so going back to what I said in the beginning, homeomorphism here is an equivalence relation between topological spaces, and diffeomorphism is a stronger equivalence relation between differentiable manifolds, which includes homeomorphism, and it's stronger than that. First of all, there should be a homeomorphism, and then there should also be that homeomorphism should also be differentiable, which we couldn't define earlier. Now, because of the atlas, we can make sense of that second statement. Very good. Now, I was asked, I think last time, that, what is known about some common manifolds that we might talk about. And so I looked it up so that I don't tell you anything wrong. And the interesting thing is that among spheres, the one sphere, is just a circle. Two sphere is the surface of a sphere. S3 is a three sphere. That's not so easy to visualize, but basically it's an equation in four-dimensional Euclidean space. You can think of it that way, of the set of points at fixed distance from some origin. And like this, S4, S5, and S6, okay, all have a unique differentiable structure. That means if you define them as topological spaces, then the possible differentiable structures you can put on them are only one. That doesn't mean that there's only one way to put charts or make an atlas, but it means that all possible atlases you can put on those spaces are mutually compatible. Okay, and remember that differentiable structure is an equivalence class of atlases. So there's only one equivalence class for these cases. However, very beautiful example, S7, due to John Milner, I think 1956, I could have got the date wrong, but I think it's 1956, admits multiple differentiable structures. Showing this and going into any explanation about them is well beyond the scope of this mini course, but it obtains multiple differentiable structures, and Milner actually showed that there are at least 7. Okay, so a lot of 7s. S7 has 7 differentiable structures, but turns out it's not actually 7, it's larger than 7. And now it's proved that there are actually exactly 28 differentiable structures. This is just to show you that we can't just look at this definition and guess out of our top of our head whether there will be or won't be multiple differentiable structures. So S1 up to S6 all unique. S7 has this. S8 is again unique. S12 is again unique, excuse me. So there's a certain set of numbers for which it's known that the sphere has a unique differentiable structure. There are others for which we know that there's more than one, but we don't know how many, and so on. Okay. Among Euclidean spaces also, there's an interesting one. I think I misspoke. I think S4 is not settled yet. Does anyone know who is here? I think for S4, there's still a question. I don't think it's proved that it's unique. I think for the others, it is proved. Okay, for Euclidean space, the result is even more tantalizing. Rn has a unique differentiable structure for all n not equal to 4. But R4 has a continuous family of differentiable structures. That means that I can put an atlas on R4, and then if I'm clever, I can deform that atlas continuously into different atlases which are not differentiably equivalent to the original one, okay, whose charts are not compatible with the charts of the previous one in the sense of differentiability. So, well, it's a weird result. I freely admit it's very tantalizing, but many things are known, many things are not known, and you should look up more on this on the internet. These are called exotic manifolds. For example, the Wikipedia page for spheres is called exotic spheres. So you can look up exotic spheres. And you'll find whatever is the current information. And then for more than that, you can look up books by various mathematicians. Okay. So now I'm a bit confused about S4 because even in my book, I've written that Sn for n less than or equal to 6 has a unique differentiable structure. But I think I read today, okay, I was in a hurry, that S4 might still be open. I don't know. Anyway, it's not important enough to go into. Okay, now one more thing before we embark on an important topic of calculus on manifolds is orientability. I'm going to be very brief with this. So generalizes, or rather how do we define orientation for a differentiable manifold? Now, just to give you some examples to show you that there's something interesting here. If the manifold is familiar, if manifold was an embedding in 3 space, then we have an intuitive idea, and that idea, as usual, has to be kind of employed to give an intrinsic definition just using differentiable manifold theory, as we've been discussing. Supposing it was an embedding in 3 space, then let's look at 2 examples. One is the 2 sphere. And on the 2 sphere, you know that there's a concept called a normal. There's tangent and there's normal. Tangent also we'll come to, but right now we are focusing on the normal. And you know that the normal can be defined, let's take a unit vector, such that it points outward everywhere. We could also reverse its sign and then it would point inward everywhere. So this concept that it's everywhere outward endows this manifold with an orientation. Okay, so an orientation is the concept that there's a sense of, there's a meaningful sense of normal vectors being outward. Okay, what shouldn't happen is that I start with an outward normal vector, I move it all around the manifold, and when I come back, that same vector is pointing inward. That does happen in some other space. This is S2, but there's another space very famous in topology called the Mobius strip. You probably know what it is. One way to define it is to take an ordinary strip like this, but now I identify the ends with a twist. So I identify along the arrows. So I take this, twist one end, and then I take it and loop it back. So it's like a loop. My drawings are always terrible, I warn you of that. It's like a loop, but at some point it crosses over like that. So it's like a belt which has got one twist in it, precisely one twist, not multiple twists. Okay, now in this thing, I'm sure you've seen one, or you can easily make one for yourself with your belt if needed, or with any strip of cloth or paper. Now, supposing I take a normal which looks outward, I'll just define it to be outward by convention. See, outward doesn't have that much of a meaning in general. It's just one particular direction. And I take this normal and transport it all around the Mobius strip. like this. Then when I come back, the same vector is pointing this way. So normal after transporting around comes back reversed. Okay. So if this was the original normal n1, eventually I get minus n1 after going round. And the reason for that is the twist. You see that there's a twist here, and that twist is causing the normal in a continuous manner going around this manifold to come back to minus itself. That means that I cannot describe one side. The strip doesn't have one side. And actually, this is another fact that if you take some kind of a paintbrush and start painting the surface of a Mobius strip and keep going till you come back to where you started, you would have painted the whole thing, not just one side. While if you did it with a belt, which is more like a cylinder, if you paint one side and come back, you will still not have painted the other side. You have to do it twice. Okay, but in this thing, you basically paint one side, and when you come back continuously, you're actually on the other side. So you keep painting, and when you come back, you're on the first side. It's a very beautiful thing, and anybody, I'm sure everybody who's here knows what's a Mobius strip and has played with it. Anyway, so the conclusion is that S2, the two sphere, where the normal everywhere outward exists, is called orientable, and Mobius strip is called non-orientable. Okay, if it's orientable, we can give it an orientation by saying, okay, this side is one is outward, this side is inward. That's our choice. But if it's non-orientable, we can't do anything. Okay, so we can't give it any orientation except in local patches. As a whole manifold, it doesn't have an orientation. Okay, but all this relied on having a two-dimensional space that we can visualize in 3D, but that's exactly not the point of our definition. Our definition of differentiable manifold is pretty much any topological space with an atlas. So how will I define it for that? Okay, so in general, this was only a couple of examples. In general, I don't even have a definition as yet. So let me give you the definition. And for that, I'll take my manifold M, and I'll take a part of it, U, and as usual, I'll map it with two homeomorphisms, which are two different charts, phi alpha and phi beta. And this one goes to, let's see, oh, sorry, sorry, that's not exactly what I do. Let's do it a little differently. I did this last time actually, so I'm just repeating. Let's have one chart with open set U alpha and an overlapping one with an open set U beta. Okay, so U alpha of course goes to phi alpha of U alpha, which is a set in Rn, and U beta goes to phi beta. Phi beta is a different map, so it goes to phi beta of U beta, which is also in Rn. Okay, good. Now, we already saw last time that there's a map phi alpha composed phi beta inverse from the intersection U alpha intersection U beta, for which I can do both things. I can use this map to come here, and I can use this second map phi beta to go here. And so this is the structure we discussed last time. So actually, this phi alpha phi beta inverse takes me from okay, maybe the other way around. Phi beta phi alpha inverse takes me from the left space phi alpha of U alpha to the right space phi beta of U beta. Very good. Okay. Now this map, as I emphasized last time, is from Rn to Rn, subset of Rn to a subset of Rn. So because it's Rn and Rn gives you coordinates, which are the usual Cartesian coordinates, this map can be described as f from xi, which is a point here, to yi, which is a function of x1 up to xn. This is the usual thing in physics which we call change of coordinates. Okay, and now these old coordinates x and new coordinates y, between them they have a Jacobian. Remember, this map has to be invertible. That's the whole point, because it's nothing but the homeomorphism phi beta composed with phi alpha inverse. And because they are homeomorphisms, they are invertible in a continuous way. And then because these charts are compatible, they are also differentiable. Okay, so this map is, in the ordinary sense, invertible as well as differentiable. And so I can take the Jacobian del xi by del yj, performing ordinary partial differentiation in Rn, and then take the determinant. Okay, and now this concept allows me to decide whether a manifold is orientable or not. So the definition is that a manifold is orientable if, now follow the definition carefully, we can choose an atlas such that on every overlap, I gave you only one overlap in this drawing above, but should be true on every overlap of charts, the map phi beta composed with phi alpha inverse from Rn to Rn has a positive Jacobian determinant. So this del xi del yj should be, it should be possible to choose on every overlap so that it's positive. Okay, if we can, then the manifold is orientable. If we can't, that means that we cannot find an atlas such that this map always has positive Jacobian, then it's non-orientable. And in the book, I've given examples which show that a cylinder, so cylinder is like this, and as you might guess, this is orientable. And I've given explicitly the charts, okay, the charts for, you know, the cylinder, like just like a circle. A cylinder is nothing but direct product of a circle and a little strip in the vertical direction. So I can draw my open sets on that. I can make my charts which take me to R2 because it's a two-dimensional surface, and then I can consider, let's say, half the cylinder or all of the cylinder minus one end, and then all of the cylinder minus the other end, and then look at the overlap functions between these two charts, and I'll find that their Jacobian is very simple. This is a very simple space. The Jacobian can actually be chosen just to be 1. Now, supposing so in fact, in practice, we can choose Jacobian just to be 1. So we can choose an atlas for which the Jacobian is 1. But now if we apply the same logic to the Mobius strip, which like this, then it's non-orientable. And what we find is J equals 1 on one overlap, but it's equal to -1 on the other overlap. So that's the key difference. Okay, and with this, I can these examples are still those which we can visualize in 3D, but now it doesn't require any visualization. All you need to do is to find the charts and write this function xi going to yi. And once you know that function, you can compute its Jacobian determinant and show that it's everywhere positive. Okay, it need not be constant in general. We only want the sign to be positive. For simple cases, it may be constant if the overlap functions are linear. Good. Okay, so that concludes the discussion of differentiable manifolds for their own sake, and we'll now turn to an important topic called calculus on manifolds. So before that, I'll look at the questions. Yeah. Yeah, RM and Rn are not homeomorphic. That is correct, Shivani. I think you forgot something we are trying to do. The composition psi f phi inverse is not a homeomorphism. It was never supposed to be a homeomorphism. You forgot one thing, phi and psi are homeomorphisms, but f in general is just a function from a manifold to another manifold. So this illustrates a point. Often when we hear a lecture, we sort of forget all the ifs and buts in every sentence. But if you want to get the most out of this lecture, you need to realize that when I was talking of this two manifolds and say that the function is differentiable, I never said this function has to be a homeomorphism. Okay. Later on, when I said the function is a diffeomorphism, that time this function has to be a homeomorphism. But now it means that m is equal to n. This can't be otherwise. It has to be that m is equal to n. So two manifolds can only be diffeomorphic if if they have the same dimension. Two manifolds which don't have the same dimension cannot be diffeomorphic. But two manifolds which do have different dimensions nevertheless can admit a function between them. Such a function between manifolds of different dimension is certainly well defined. It depends what you want to do with it. We won't in general assume it's a homeomorphism. Yeah. Supposing we have two different differentiable structures, will we talk about two kinds of differentiability? Yes, we will. One is differentiability as defined by charts of one atlas, and the other is differentiability as defined by charts of the other incompatible atlas. The differentiation will always be carried out in Rn. Okay, differentiation of functions is always done in the map from Rn to Rm. But the problem is that assigning the derivative, saying that this function is differentiable means this function is differentiable, okay, requires knowledge of phi and psi. Without that knowledge, I can't relate any property of this function to a property of this function. Okay, so it's only given phi and psi that I can define this function to be differentiable if this function is differentiable. Now, if I were given different phi and psi, which are not compatible with this one, that is incompatible charts, then different class of functions would be differentiable on the original manifold, namely the ones which these phi and new phi and psi map to differential functions from Rn to R. Yeah. How can we talk about the composition being differentiable or not when it contains f whose differentiability is not defined? Because the composition is a map from Rn to Rm, Rn to Rm. Any map from Rn to Rm can be differentiated. That's how we can talk of the composition being differentiable. And we use that to say that the function f is differentiable. We don't have any other way to differentiate the function f. Again, somehow I have the sense that you're taking my words like, when we talk to people in a cafe, we just then get the general sense of what they say. That's not how you should take a lecture, I feel. I know it's difficult in a short time, but you can't miss any ifs, ands, and buts, least of all in a lecture on mathematics. That's just a fact. Otherwise, you'll just get confused. Not all manifolds have a metric. There absolutely no metric has been mentioned by me, Abhishek, today nor yesterday. In fact, this is the 6th or 7th lecture, and I still haven't ever mentioned a metric in this context of manifolds. How is it possible if the manifold is defined to be chart-wise homeomorphic to Rn, but Rn does have a metric? I don't have to take every property of Rn to the manifold, do I? I might not. I'll come to it. Be patient. 4 dimensions have infinite differential structure, and I think this is R4. R4 does have infinitely many differential structures. Do we have any concept of convexity and smooth manifolds? Okay, yeah, I think this is not relevant to the discussion because, yeah, we could do all what you say, maybe, but I don't have time for it, sorry. Meaning of orientability is clear, but how it relates to positive Jacobian is little unclear. Thank you. That's a good question, Dharmaraj. I didn't exactly relate it. Concept of orientability intuitively is clear, but I think the best way to see that positive Jacobian is just think of a one-dimensional case. Okay, think of a map from some one-dimensional manifold like a circle, and imagine that in one chart the coordinate is x, and in the other chart it's minus x. Y is minus x. Okay, then the Jacobian is -1. Okay, now it's quite easy if you make a few drawings that in the chart where it's x, the normal. So for example, take a circle embedded in a plane. Okay. Now the outward normal in the XY coordinates on the plane is outward, obviously. Okay. Now if I flip the coordinates to minus themselves, that normal will go to inward. Okay. So the derivative of x with respect to y or y with respect to x exactly is going to be the Jacobian. So I can't do more than that here in detail, but you should see that, you know, the derivative of xi with yj, uh, okay, yeah, captures the concept of orientation. Maybe try some examples, maybe it'll emerge. There are two examples given in the book at least, in some detail. So take a look at those and see how these two map. Uh, yeah. Achal, Vinod, could I provide a visualization for a particular differentiable structure, or it's just a mathematical concept? So now, good question. It's a good question, but just think of it this way. You know, Riemann lived and died, and he didn't know that there can be more than one differentiable structure. Okay, if it was obvious, of all the people, super smart, Riemann would have found it obvious. Okay, as well as other people who worked on topology and geometry and manifolds. So Riemann got to be, you know, got to develop manifolds with metric in great detail, but he never saw the obviousness of multiple differentiable structures. It was only 1956, that's not so long ago, that the first example was constructed by Milner. Till that time, the question was open whether there can be more than one or not in general. It was an open question. By constructing an example, he showed that yes, there can be more than one differentiable structure on the same topological space. Very strong new result. It's the kind of result that, you know, if you can prove that once in your lifetime, then you can go to your grave happy, because you have changed the whole subject, the whole way people think about the subject. So, short answer to your question is that it's a mathematical concept as we defined it, and there's no intuitive way. But if you want some details, you could look at Milner's construction of exotic seven sphere. Just pick one of his seven spheres. He actually tells you how to get it. So his construction involves, well, it involves fibration, so which we haven't studied yet. But maybe if you're patient and once you learn fiber bundles, what he does is to combine an S3 and an S4 in a special way, which gives you S7. And then he shows that if before combining them, I do some particular thing to one of to the S3, so and then I can get this exotic S7, something like that. Okay, it's not that difficult in formulas, but it's definitely nothing intuitive. Yeah, yeah, very good, very good. Okay, now we move on to calculus on manifolds. And here, now see, all this time, we've been trying to focus on the manifold. But now we really focus on what can you, so basically, we now focus on, focus on functions, curves, tangents, vectors. You see, all these words we have studied in calculus. Okay, they are not words in calculus. Everything is very precisely defined in calculus. Gradient of a function, which is also known as directional derivative. So all this is known in ordinary calculus. But in principle, we don't know much about this, even on a surface as simple as a sphere, okay, a two-sphere. What is the tangent of a two-sphere? Now, I know what you'll say. You'll say the tangent is the plane which just touches the two-sphere. And now you'll see a problem, a potential problem in that statement, because a two-sphere on one hand can be described as a submanifold of 3 dimensions, and then we can talk of the tangent as the plane which just touches the surface of the sphere, all right. But supposing I didn't know that description of S2 and I only knew its description in terms of an atlas. So I knew its description as a differentiable manifold. Now, how do I talk about tangent? Tangent of these kind of spaces looks like something which goes outside the space, right? But that's not fair, because in principle, a manifold is just what it is. It doesn't have to be embedded in anything. There's no outside for it to go to. So we need a priori definitions of all these concepts for manifolds, and that's called calculus on manifolds. There's a lovely textbook by Spivak called Calculus on Manifolds. It's very short. That's one of the things I used to love about it for manifolds. So a priori definitions of these concepts for manifolds. Good. And how are we going to do it? Well, you already guessed it. Okay. How we do it is always the same. We take a manifold, we use the fact that it has a chart. We follow the chart to get into Rn. In Rn, we know all these concepts. We take them from Rn and take them back to the manifold by the inverse homeomorphism. Those are the words. Now it's just a matter of doing it. But we find some very interesting things which we might not have been prepared for in Rn. And let's do it. Okay. Good. Okay. So now let's consider my manifold M. And let's consider two different charts again. And this time I'll label things a little differently. Instead of giving you the homeomorphism explicitly, I'll just assume that this open set, the first one, U1, is described by a coordinate system X. This is a quick way of saying that I have a homeomorphism which maps U1 to a subset of Rn, and there on that subset, I use a coordinate system X on Rn. This other open set U2, I'm assuming is mapped to a different coordinate. It's mapped first of all by a different homeomorphism, okay, because it's a different chart, and that different homeomorphism takes it to the Y coordinate system. So, by the way, in principle, there's no reason that U1 and U2 have to be disjoint. They could be the same open set, and two different homeomorphisms take us to X coordinate system and Y coordinate system. That's also allowed. This is the most general scenario where they overlap and we have two homeomorphisms, one taking me to X and the other taking me to Y. Now, supposing I have a function from this manifold to R. Why R? This is a very special case. Before this, we discussed functions from manifolds to manifolds. But of course, R is a manifold in the usual topology, and I'm picking this out. Now, let's try to understand, first of all, why R. We are going to discuss that for some time. Later, we can generalize it. Well, just think of manifolds that you know. One of the best non-trivial manifolds you know is the surface of the Earth. Okay. Now, at every point on the surface of the Earth, there is a temperature. Okay, what is that temperature? It's a function from the surface of the Earth to the set of positive real, well, not necessarily positive, set of real numbers from minus 273 to plus anything. Okay, so temperature is an example. It takes the Earth via the temperature function to R. Some subset of R, that's all right, but it's R basically. So that temperature function takes a location like Pune and returns something like 22 degrees centigrade. It takes another point and returns another number. That's how functions work. So here's an example. So we are going to look at such functions. Now here there's a very valuable lesson which often gets lost when we teach physics of manifolds in the usual physics way, which is that if there's a point P on my manifold, regardless of how I label it, it's the same point. For example, Pune Pune isn't a point, but in very approximate sense, you might say it's a point, or you might say that the room I'm sitting in is a point on the map. Okay, it's sufficiently point-like. Now, the idea is that this point has an existence independent of whether I use X or Y or Z or Q coordinates to describe it. It's always the same point. If I change a homeomorphism from my manifold, which helps me describe the manifold, I'm not changing the point. This is very important, and I think it's very illuminating. For this reason, for example, in this case, temperature at P is a well-defined concept. It can't depend on coordinate system. It can't be that somebody else who puts a different coordinate system on Earth finds a different temperature from the existing one. There's only one temperature and I can measure it. Okay. It follows that if this point P, supposing it were here, this is the point P. I always use P, and conveniently it also can stand for Pune. So P has coordinates xi in one system and yi in another. Then it must be the case that the function f from the manifold to R, which actually is not this function, but it's the function phi. Okay, let me say this. Let me see how I've said it here. Yeah. Okay. Okay, so what follows from saying that the temperature at P is a well-defined concept? Supposing I pick a coordinate system X, then temperature is given by a function. Let's call it f of x. Okay. If I pick a different coordinate system y, then temperature is given by a different function, g of y. But the property that these two functions have is that f of x must be equal to g of y, okay, where x and y are coordinates of the same point P in different systems. It's a very trivial statement, but it explains a lot of things. Okay, I hope this statement is clear. That because concept like temperature or any function is well defined in the sense that it takes a given point always to a given value. So the value can't depend on what coordinate system I use, but the form of the function will depend on the coordinate system that I use. And the condition or the constraint on it is that the function evaluated at the point x in Cartesian coordinates is the same as the other function g evaluated at y, where x and y describe the same point on the original manifold. So f and g really differ because of the homeomorphism in different charts. Okay, but the point is the same. This is very key, and if you want, you can look in the book for more precise and detailed description of this fact. Now, a function, now f is one function and g is another function, but really the temperature function was a single function. I keep using temperature because it's as good as considering any function from a manifold to the real line. So we say that temperature, this is well known in physics also, temperature is a scalar function. A scalar function precisely has the property that if I take its form in one coordinate system and its form in another, the two are different, but the value is the same for the same point. You might have seen it in physics by the statement. You might have memorized the statement, or in future, I'm sure you will memorize the statement that if phi of x is a scalar field in field theory, then phi prime of x prime is equal to phi of x is the definition of transformation property of a scale. Here I've tried to explain to you that this is a geometric statement. It's not something out of the blue. And what it says is that a function from a manifold depends on where the points go, not how the points are described. That is embodied in this statement. Okay, good. Now let's differentiate these functions. And we find something a little different. Okay. Now, if I differentiate f, I can differentiate, consider del f by del xi, the partial derivative of x along all the n directions xi is nothing but the gradient. And consider del g by del yi. also the gradient in a different coordinate system. Are these equal? And the answer is they can't be equal for the following reason. If I take del G by del yi, that's differentiating a function of y with respect to the y, but y itself is a function of x. Okay, that's the relation between the two coordinate charts. So this is del G of y of x, or sorry, yeah, y of x with respect to y. This is equal to, sorry, I did it in the wrong order. First, I'll use the fact that g of y is equal to f of x, this one, okay, this relation. So I'll write this as del f of x by del yi. But now my question is, how do I differentiate a function of x with respect to y? Well, x itself is a function of y, so I can differentiate del fx with respect to xj, multiply it by del xj with respect to del yi, and sum over j, which I'm not going to write in the future. This is chain rule. Now notice that I've answered this question. The question here was, are these two things equal? One of them is here, the other one is here, and the answer is no, they are not equal. They are related by this factor, which is actually something that, sorry, one is here and one is here, and no, they are not equal. They are related by this multiplicative factor, and so they're simply not equal. Okay. So this is a statement about the transformation of gradient. So if you like, this is the rule to transform gradients. So this is one rule. It's a very important rule, and we'll just mark it as one and go on. And then we'll come back and we'll study it a little more in detail later. Okay, now let's look at the second thing. The second thing, so the first thing was achieved by taking gradient and looking at the relation between the x coordinates and the y coordinates, which I emphasize are related by this thing. So it's just this homeomorphism inverse and then this one. Takes me from x to y or from y to x. I can go in either direction. Okay. Now the second situation I want to consider is consider a curve on M. So a curve on M is, for example, a path. It might be the path I take when I drive to office. So it has a starting point, which is my home, ending point, which is my office, and point-wise, it traces the points on the surface of the earth, which I cover when I go from home to office. That's a path. Again, remember, the path has a meaning regardless of what coordinate system I use. It's actually that path that I personally experience when I travel to office, and it doesn't become a different path if you use some other coordinate system to label it. Okay, so this curve, let me label by P of t. So this generalizes my original point P to a time-dependent set of points. I can think of t as a time such that t equals 0 maybe is the time I leave home, and t equals 10 minutes or whatever is the time at which I reach office. So t is a parameter. So it parameterizes the path. Okay. Now, admittedly, t also is arbitrary. I can choose one t, somebody else could choose a different parameter t. And we've seen already in the context of homotopy that for many situations, if you have a parameter t, somebody else might choose a different one, but you get similar mathematical results. Okay. But now we are going to, even though it's arbitrary, we are going to fix it. We are going to choose it, and we are not going to change it when we consider different coordinate patches of my manifold. So P of t is considered given once and for all. The path starting from one place, ending at another place on the surface. Okay. Now, supposing I take the homeomorphism, let's go back here. This is phi alpha, this is phi beta in my usual thing. Okay. And Supposing I take the image x of my point P, but now my point P is moving on a path. So obviously x will also move on a path. So corresponding to this, I'll get xi of t in x system and another path yi of t. So the same path, but its description in the y system. And now the question is, what is the relation? Okay, well, let's try to differentiate these functions with respect to t. So why would I do that? Well, for example, if I want to ask questions about my velocity as I travel from here to office, I don't know what to do with this quantity p of t, because p is an abstract point. It's not a number. It just labels the actual point on the Earth's surface. T is a number, but how do I differentiate an abstract point with respect to a number? I can't. So I have to use a chart, and I can use x, in which case I'll find that my velocity is dxi by dt. I'm just calling it velocity. It's the rate of change of the coordinate of the point as the point moves on the manifold. Similarly, here I have dyi of dt. It's the rate of change of the coordinate of the same point as it moves the same way, but in a different coordinate system. And what is the relation? Obviously, they are not equal. Instead, the relation follows again by chain rule that dyi by dt is del yi by del xj dxj by dt. Okay, and this is relation 2. Now let's look at relation 1 again and look at relation 2. In relation 1, we had a function taking the manifold to numbers, and when we differentiate that function in one system or another system, we get this extra factor del xj by del yi multiplying it. Okay, so that's one kind of transformation rule. Here, on the contrary, we didn't have any function. Instead, we had a path. We specified the path, and now we considered how the path looks in one coordinate system and another, and we differentiated it with respect to the parameter t of the path in both coordinate systems, and by simple chain rule, we got this result. Okay, and this one has also this extra factor del yi by del xj. Notice that it's the reverse. Here I use the derivative of y with respect to x, but here I got the derivative of x with respect to y. So there's a meaning in these two statements. Let me summarize them here and then try to extract the meaning. So the first one was del g of y del g by del yi is equal to del f by del xj by del yi. And the second one, it's written just above, but anyway, is I by dt is equal to del yi by del xj xj by dt. So this relates, if you like, this relates velocities. If you want a quick way to remember, this relates gradients of a function. It's difficult to talk of a gradient unless you have a function whose gradient you're talking about. This one relates velocities. I'm just using that as a term with respect to the parameter t for a curve, on a curve. Good. So we have two results, and these are useful. Now let's give some words to these. So the first thing is that this one is called the tangent vector to the curve P of t in the x coordinate. And this obviously is also the tangent vector, but in the y coordinate. The relation between the tangent in x and y coordinates is given by this formula. Okay. As far as the gradient, we haven't yet given it a name, and we'll come to it in a minute. Let's focus on the tangent vectors because these are interesting. First of all, a non-trivial statement here is that this concept of tangent vector, which is take a path on the manifold, map that path onto using your chart onto Euclidean space, and then differentiate the coordinate as it varies with t, and just call that a tangent vector. It's not at all obvious that this is a meaningful definition of tangent vector. Let's first recall a few things about what we learned about curves in the plane. So plane curves, at least I don't know about you, I learned them in high school. So the idea was that you have some curve like that, and it's given by a function x of t and y of t. Sorry, y will be confusing in this context. Let me call them x1 and x2, x1 of t and x2 of t. Okay. Now I take dx1 dt and dx2 dt, and this readily can be seen to give me a vector which has this appearance. It just skims the curve at any given point. Okay. The problem here is that this relies on embedding this curve in the plane. That's why it's called study of plane curves. But we don't always have that possibility. Okay, so what we've done now is slightly different from this. Notice that this curve had x1 of t and x2 of t. Okay, I had to give you two functions, but the original curve in the original space had on. Okay, how to say it? No, this is fine. Sorry, I take that back. So this is how I define the tangent vector in calculus. Okay, no, actually, I think I said just too much. This is how I define the tangent vector in calculus. And I'm doing the same thing because dxj by dt or dyi by dt are how I would define the tangent vector in calculus for a curve on the plane or in Euclidean space. The only new thing I'm saying is that this is a tangent to the original curve. Okay, so there's the key new thing is to say that the tangent vector as calculated in Euclidean space can be identified with the tangent vector to the original curve P of t, which was sitting in an abstract manifold where I didn't have any independent way to define the tangent vector. So the only question that arises now is, supposing that manifold is like a two-sphere, I can do all this. Okay, I have a curve on the two-sphere. I map that segment of the two-sphere, a small patch of the thing, onto R2. In R2, my diagram will look exactly like this. In this, I carry out this derivative. I get the velocity vector, and I say that this is the velocity of the original point on my two-sphere in x coordinates. But you may have chosen y coordinates instead. You'll do the same exact thing, but you'll use the other map, okay, the y map, and you'll carry out this differentiation in y coordinates, and you'll get your result. How are our results related? They're related by this formula, formula 2. So this is one of the key results. And the question of whether this captures the concept of tangent to a sphere in R3, I'll leave it for you as an exercise. For that, you need to do the following. You'll get, if you do this process for a curve in S2, you'll get a vector, and that vector in 3 space will look as if it's grazing the surface of the sphere. That's an extra exercise to be done. Okay. I'm sorry, I possibly could have said this in fewer words. In fact, in the book, it's said in much fewer words. Okay. Now, some properties of tangent vectors, which are not obvious. One, linear combination of two tangent vectors is again a tangent vector. Now, this is a curious fact, but let's see what we mean exactly. Let's start with our example manifold, say the sphere S2, and we have our curve, okay? And this is our favorite point, P. Now, this curve is P of t. Actually, now, yeah, okay. Let's call this curve, let me not have a favorite point. Let's just call this curve P of t. Now let's have another curve Q of t, which intersects the first curve at this point. So let's imagine we have this setup. So now there are two different tangent vectors defined by these two curves at the same point. One of them is obtained by, so I take this whole structure and map it onto R2, there I differentiate, and one of them I can loosely think of as this vector, and the other one I can loosely think of as this vector. Remember that the vectors are in R2. They are called tangent vector to the sphere, but they are actually in R2. Now in R2, if I have two vectors, I can take the linear combination and get a third one. So what I'm doing is taking this curve, mapping it to R2, computing the tangent, taking this curve, mapping it to R2 by the same map and computing the tangent this way, and then taking a linear combination, and I get a vector like this, and I can take this new vector and map it back from R2 onto my manifold. So I'll get something like this, but it's not a tangent to either Q or P. So why am I saying it's again a tangent vector? And the answer is very simple. I can make a curve for which it's the tangent vector. Okay, so the statement is that I can make a curve, a new curve on the manifold M for which the linear combination is a tangent vector. Remember, in defining tangent, we started with a curve, but we never said that we only need one curve. We can consider all possible curves in the manifold, okay? And if we have some of them, we can take the tangents to those, take linear combinations, and then generate new curves accordingly. And from this, we can conclude that linear combination of two tangent vectors is again a tangent vector. So the tangent space is a vector space. So this leads us to the concept of tangent space, which is the vector space of all tangent vectors to all possible curves through a given point. So in this sense, remember that this will be the tangent space at a point. Even though there's a curve going through the point, the differentiation and evaluation of this dxi by dt is done at a particular point, and there I can consider multiple curves passing through the same point, write the dx by dt for all of them, and that whole set of vectors will give me a vector space. Now, since it's a vector space, it really doesn't look like the manifold. So the tangent space doesn't look like the manifold. The manifold is lumpy, bumpy. It has some differentiable structure and some charts. The tangent space is flat. So because I can add two things and I get a third one. Remember, for topological spaces, I couldn't add two elements to get a third one. For manifold also, I cannot add 2 points to get a third one. But now for the first time, I can add two objects to get a third one, and these are the tangents. Okay. And this may take some, you may need to focus on this construction a little more carefully. Again, it's in the book. Basically, I've given a algorithm to construct the curve in the manifold for any tangent vector in the Euclidean space by just following the homeomorphism backwards. Okay, good. Okay, and now there's a last thing to be done. So if you now recall, now we'll connect these two things. In the first one, we differentiated functions. In the second one, we differentiated paths. Okay, but now there's a third thing I can do, which is sort of a combination of the two. Supposing we are given a function f from M to R, then we can compute df by dt along a path. So in this third one, I'm considering that there's a function and also a path p of t. Both things. Okay, and I want to compute how the function changes along the path. Not very difficult to find an example. I mentioned temperature as a function on the surface of the earth. Now, as I go on the path from home to office, I could have a very sensitive thermometer and it will measure exactly at any point, it will measure dF by dt. It will tell me how the temperature is changing for as I traverse the path. Now notice that if I really do this experiment as a physicist, let's say I walk from point A to B holding a sensitive thermometer, is going to give me readings. Those readings are going to tell me dF by dt, right? I can take readings at two neighboring points, plot them, and then find dF by dt in the usual way that we do in calculus. Notice that no coordinate system came into this discussion. dF by dt doesn't contain any reference to an x-coordinate system nor a y-coordinate system. It's just a differentiation of a function with respect to a parameter along a path. But it requires more data. It requires a path as well as a function. In contrast, the gradient has reference to a coordinate system. That's why we have this equation here. And the velocity of points on the path also has reference to a coordinate system. That's why we have this equation here. But dF by dt has no reference to a coordinate system, and I can rewrite it in a very nice way that dF by dt is the same as dF by dxi by dt. Chain rule. The function I evaluate in my coordinate system, so I get this coordinate dependent quantity for the gradient, and then I evaluate the velocity in my coordinate system and I get this for the velocity. But notice that this depends on coordinate system. And this also depends on coordinate system. But this does not depend on coordinate system. This is a very, very useful result because supposing this whole thing was being done in the y coordinate system, I would simply have written that dF by dt is equal to del g by del yi dyi by dt. Okay, I would ask what is the temperature function in my new coordinate system yi, and I would take its gradient, which is the first factor, and multiply it by the velocity of the point in that coordinate system. And these two things have to be equal because both are equal to the left side, which doesn't depend on coordinate system. So these two things just have to be equal. And there's no surprise there. In fact, you can explicitly verify from these two laws that if I take dg by dyi and multiply it by dyi by dt, and if I carefully also take the same on the right side, taking care of the dummy indices, then this factor and this factor actually cancel out and I get the equality that I want. Namely, product of this and this is the same as product of this gradient and this velocity. Okay. And this allows us to introduce a notation which is not used that much in physics, but is very popular in mathematics. And let me try to do it. So let me write dF by dt, the same expression, but in a slightly more suggestive way as dxi by dt del by del xi on f. I've just taken this equation and rewritten it by taking f outside. Okay, and this, as you can see, is a differential operator. Okay, now this is true for every possible function f. So I can also think that d by dt, the derivative operator along the path, is the same as dxi by dt del by del xi. Okay, and this is a very useful relation. What we can basically say then is that this operator is some kind, okay, so what we define now is that this thing is called a vector field. It's basically a differential operator which, when it acts on a function, will transport that function along my given path. Okay, and this is nice. The reason this is nice is Just this velocity or just this gradient operator were not coordinate invariant, but this is a coordinate invariant quantity. Because I can as well define d by dt as dy by dt, d by dy. Now it should act on functions g of y, but the operator looks the same, so it's coordinate invariant. So this brings us to a very nice concept, which is the concept of vector field, which tells us that there's a differential operator, the gradient, dotted with something which specifies the instantaneous velocity along a path. So in this process, we got rid of the function. Now the last thing we want to do is get rid of the path. Got rid of the function. Okay, but instead of writing this formula above which involves a function f, I wrote a formula for an operator which doesn't involve f, but it still involves t, so it involves the path. So now the next step, which is the most logical step and which completes this description, is that an arbitrary vector field, this is the vector field along the curve that I gave you. That's why it has the t dependence. An arbitrary vector field is any differential operator of the form ai of x d by dxi. I simply dropped all reference to the path, and instead of dxi by dt, I just wrote an arbitrary function, arbitrary set of functions, actually ai of x, okay, on the manifold. And what did I gain by doing this? Well, first of all, given this ai of x, I can always reconstruct the path. What should I do? ai of x at a particular point, I'll write it as dxi by dt and draw the path for which that value of ai is the tangent vector to an infinitesimal amount. Then I'll go to the next closest point, and it's basically like integrating a function. So the path will be like an integral curve of this set of functions. So we'll call this, our notation will be that x equals ai of x d by dxi is a general vector field, arbitrary vector field. So just to recap what we did, so first we considered gradients with change of coordinates in this way. Then we considered velocities with change in this way. The problem was that gradients require use of a function, g or f, and velocities require use of a parameter, t. Then we noticed that the derivative of a function with respect to t, which involves both these quantities, the function and t, can be written in this way. Then we dropped the function by rewriting this as a differential operator in the abstract, this one. And finally, we dropped the velocity by saying, well, who wants to specify a curve? Let's just write any arbitrary set of n functions ai of x in my coordinate system, and they will specify a curve on the manifold by just lifting this tangent vectors point by point back onto the manifold. And this is what we are led to. In physics, the last thing to be said, in physics, ai of x is called a vector. For example, your electromagnetic potential is called a vector field. Okay, I could run over space-time indices, and then this would just be our familiar photon field, a mu of x. Okay, but in mathematics, it's more convenient to write it always with d by dxi, multiplying it as an operator. Because once it's a differential operator, it's coordinate independent. In just a or I of x cannot be coordinate independent. In fact, it will transform the same way as any velocity. And velocity is transformed according to our equation number 2 over here, this one. Good. So now let's take questions. Yes, Agam, yes. The results for tangent in x and in y are related this way because they describe the same path in m. Absolutely. Can we say the tangent vector we have defined is the tangent vector, say, on the sphere without the normal component, since we refuse to look at it in embedded ways? Yeah, but you know, it's yeah, but the thing is, it's not on the sphere either. The tangent, this vector space, doesn't live on the sphere. maybe I can give you a little better picture by saying the following. Supposing I pick a point on some manifold which is embedded in R3, and I take a little tiny separation of two neighboring points. Then the line joining them, drawn on that manifold, looks like a vector. Okay, but now if I take finite separation of points along a curve, that line joining them doesn't look like a vector anymore. In particular, I would have to paste it on the surface of the manifold, and now it's not a linear object at all. So instead, a vector is an abstract object, okay, which can have any length I like, but which is based at a given point. It's not based at multiple points. So it's not really a vector on that space. It's a vector in the tangent space, and the tangent space is an auxiliary space. It's not part of the manifold. It's another space, but it's by definition, it's a plane or it's a linear space. So if it's a two-dimensional manifold, the tangent space is a plane, and it's called tangent plane. But it's really a plane. So you have to always imagine that it's an auxiliary construction in which the vector doesn't actually live on the manifold. That's very important. To define a tangent, we just use coordinates, while defining gradient, no. Dharmaraj, that's not true. To define a tangent, we use coordinates and a curve, P of t. And to defining gradient, we used an arbitrary function. That is true. So our tangents, no. Tangents are not more related to the manifold than gradient. Both of them, as we defined them to start with, involved something arbitrary. In the first case, the arbitrary thing was the function itself, f. Okay, it wasn't just a property of the manifold, it was a property of the manifold. The gradient was a property of manifold and a function. You can drop the function, okay, but you have to be careful to drop it in a coordinate independent way. And the precise way to do that came from this concept that neither the gradient of a function nor the velocity in my coordinate system are coordinate independent quantities. What is coordinate independent is the variation of a function along a curve. That's coordinate independent, because df by dt, look at it, it doesn't have x or y anywhere in it. It's just df by dt. But because it can be written like this in one coordinate system and this in another coordinate system, so now I can remove the function and say that this is the vector field. So yeah, I wouldn't say that tangents are more related than a gradient, yes. The linear combinations, Agam, yes, they are in Rn. By df by dt, do I mean d by dt of f composed with, I guess f composed with p? I'm not sure what that means. It's d by dt of the coordinates for f. Okay, so well, it's exactly what I've written here. Actually, sorry, no, even that was not a correct statement. Df by dt, okay. Df by dt is literally the change of a given function as I travel along the path. I gave you that example on purpose, that here I am going to my office and I'm experiencing a temperature, okay? No mathematician can tell me what temperature I'm experiencing. Only a thermometer can tell me that, right? Nobody's coordinate system is needed for that. I'm there, I'm actually traveling, I'm actually holding a measuring equipment, and I'm measuring temperature. What are the arbitrary things in my process are, well, I chose to measure temperature, which is a given function, and I chose to measure it along a path, which is the path I take to office. But I didn't specify x coordinate or y coordinate system. No coordinate system was specified. So df by dt is literally the change in a given function as I move along a path with a given parameterization with no reference to coordinates. This is very important. It's a real, if you like, it's a real thing. One of the most important lessons of this concept of manifold and more generally also of general relativity is that real things are real regardless how you describe them. That's actually one way of saying the concept of relativity. Okay, the things which are actually happening, the things which are actual experiments, okay, they return the same result regardless how you choose to define, to describe them, what formula you choose for them. As Einstein put it, the laws, the equations of physics are the same in all frames. It's the same statement exactly. So df by dt is very important to understand that it's not a statement about any coordinate system. Maybe I misunderstood the question because he said something like df by dt. Um, do we mean d by dt of circle P? I didn't really understand what circle P means. P is a point. Yeah. Does AI of X need to be continuous for it to describe a path, Agam? Well, if it's discontinuous, then it describes a discontinuous path. You can always have a vector field and then you can argue whether that vector field is discontinuous or continuous. So for now, let's allow all AI of X. And then when we want to make it continuous for some application, then we'll say so. Does that mean a vector field requires AI to be continuous? Yeah. Okay, good. So, good. Let me, actually, I didn't do the last step. That question leads me to my last step. Um, an abstract, I gave a rather long-winded definition of vector field because I wanted to make contact with the physics of coordinate system, well, physics or mathematics of coordinate systems. But for mathematicians, an abstract definition of vector field is much simpler, and actually a mathematician will tell you this right at the beginning. Okay, so notice that since this is a first order differential operator, okay, if it acts on a pair of functions, then it has the property that x acting on fg by a chain rule is xf times g plus f times xg. So for a mathematician, an abstract definition of a vector field is a linear map from C infinity functions to C infinity functions on the manifold M, satisfying x. So x is the linear map, satisfying x of fg is equal to xf times g plus f times xg. Now, if I give you this definition right off, you would say, look, this is very, very abstract. What does it have to do with real vector fields that we understand? Well, the answer is the following. First of all, it's a linear map. Okay. Secondly, in this definition, it takes C infinity functions to C infinity functions. Okay. So whatever is in X better be differentiable, this AI of X, otherwise it won't do that job. Thirdly, by specifying distributive distributive property, we are basically saying that it's a first order differential operator, because linear maps which have the property that when they act on a product of any two functions, give me the map on first function times second plus f times map on the second function is called a derivation, and a derivation is basically in some sense a differentiation. Okay, so in a sense, this is the abstract definition, and all that we did to build up to it was sort of the concrete realization in coordinate systems. Maybe this is a good point to say that not all mathematicians find this whole concept of coordinate system very useful anymore. It was very useful in the early development of differentiable manifolds and in Riemann's work and so on. But in modern mathematics, a lot of things are axiomatically written without reference to any coordinate system. And people will say that, well, if we refer to a coordinate system, how do we know it's a property of the manifold? We only want to talk about the manifold. So they are much, what I'm doing is a rather old fashioned, from mathematics point of view, definition of a manifold, but it's motivated by coordinates. And in physics, coordinates are essential because without coordinates, you can't do any, you can't write the laws of nature. You can't write, experimental laws. Yeah. Achal Vinod asked the same thing. Could I stress again on introducing the X? I think this abstract definition sort of answers the question. But if you want me to go through the steps why I introduced it, so I noted that this quantity here was a vector field along the curve. Now we want to free ourselves from the curve. Okay, so instead of specifying a curve, we simply write the same kind of object, but with an arbitrary function here, arbitrary smooth differentiable function here. And the idea here is that when I change coordinates, this function will transform in the way that velocity is transformed. So AI of X goes to, I don't know what's the best notation. In physics, we commonly use prime, not for differentiation, but for the new coordinate system. So a prime I of x prime, which is equal to del xi by del x prime, other way around, del x prime I by del xj aj of x. Okay, if x prime is y and if a prime is given some other name, then this is the transformation law from the components of a vector field, which transform exactly like velocities. So going from velocities to generic ai of x was just dropping that choice of a path on the manifold and saying, well, I can always write operators like this one, and if you want me to claim that this is a vector field along a path, I'll simply take this ai of x and I'll reconstruct the path by, I'll just write ai of x as dxi by dt for some function xi of t and integrate to find that function. That way I'll have found the path. Locally, step by step, I can always do it. Yeah. Yeah, Farman, why did we identify the differential operator as a vector field? Because, I think not, linear combinations of, so tangent vectors do form a vector space. And this is convenient because, for example, these abstract objects X, I can take two of them, X1 and X2, and just add them. Okay, but the real reason why we introduced this thing is to make capital X coordinate invariant. Capital X, unlike these functions AI, so you have two choices. The physics choice often taught in books is a vector and a manifold. Vector field is AI of X such that this transformation rule has to be specified. This is a vector field. This is how it's taught in electrodynamics. This is how it's taught in general relativity. By introducing this gradient thing, I don't have to say that anymore. I simply say a vector field is capital X such that capital X is the same in all coordinate systems. From that, it follows that it is this, but it's also the same thing for the transformed AI multiplying d by dy. It can be written in this form for some components ai of x or ai prime of x or ai prime of y in any coordinate system. So the introduction, making it an operator frees us from the coordinate system. That's the key idea. Is there a way to compare two tangent vectors at two different points on the manifold? That's a very good question, and the answer is no. You can only add tangent vectors at one point. Okay, and in fact, if you want to consider the collection of all tangent spaces on the manifold at all points, that forms what is called the tangent bundle, and that has to be studied under fibre bundles. It's a more complicated kind of space. It's a space, I'll explain it when I get to it. Yeah. So exactly as Dhruv said, they belong to different vector spaces. Okay, Arjo meant the path P. No, so, I see. See, df by dt means differentiating the function along the path P. So yes, if you are asking whether the path P is included in the definition df by dt, definitely, because otherwise what is T? F isn't a function of T. F is a function from the manifold to real numbers. Okay, now only if I put a curve on the manifold, now there's a parameter T which traces that curve. So the same function reduces to a function on that curve, and I can differentiate it on that. So in that sense, the answer to your question is yes, it is d by dt of f restricted to the curve P of t. This is correct. But of course, it is so for every curve P. And eventually, as you saw, we dropped the choice of curve by simply writing the general tangent vector field. Yeah. Yeah, Shantanu wants to know what is the vector here. It's up to you. Either, I just said there are two options. Either you say a vector is a set of n component functions, okay, subject to the rule that it changes every time I change my coordinate system. Or you say that a vector is a linear map from C infinity functions to C infinity functions, and you don't have to mention any coordinate system, but you have to give this property of the vector field that it's distributive in the sense of a derivative, that it satisfies the chain rule x of fg is xf times g plus f times xg. So which one you call the vector field is up to you. Physicists normally call this thing the vector field. As I said, in all textbooks in quantum field theory, it's called a vector field. This is the, as I said, the electromagnetic vector potential is of this form. The electric field, magnetic field, all are of this form. So physicists like to do this, but then they have to be aware that every time I change coordinates in general relativity or even in special relativity, if I go to from Cartesian to plane polar to spherical polar coordinates, the components of my vector change. Ax, ay, az are not the same as a theta, ar, a theta, a phi. Okay, but ai of x d by dxi is the same whether the x's are my xyz coordinates or my r theta phi coordinates or any other coordinates I may think of. So that's so for mathematicians, the fact that it's the same geometric object is embodied by writing this. That's very important. Is there an intuitive way to relate the notion of a vector field as the velocity profile of a fluid, Aditya? Yes, absolutely. Absolutely. The velocity profile of a fluid. So if I'm at a point in the fluid, there's a particular flow. That is the direction in which that point is going to go. So that means the velocity field of a fluid already sets up a family of curves in the manifold. Okay. So now it's obvious that I can think of, on each curve, I can think of the velocity as giving me a vector field along that curve. But since the fluid has lots of vector fields all neatly stacked on top of each other, I get a vector field in the whole fluid. That's actually very nice. So it's a very natural way to do that. You're completely right. So d by dxi are basis vectors. Yes, they are basis vectors for the tangent space. But remember one thing, if I want to generate the tangent space, then I should be at a fixed point. Then I can multiply these basis vectors by numbers and add them. So this was the general description of a vector field, but at a point x0, I have to restrict that small x to x0. So x was ai at x0, x0, just a particularly chosen point, d by dxi. And now you see that these ai are just numbers. So this is truly a linear combination of d by dxi's, and therefore d by dxi form a basis of the tangent space. Thank you so much. Basis of tangent space. Yeah. But as I allow x to vary, I get a vector field, and vector fields don't form a tangent space in the same sense. Because the tangent space is the, I mean, you can add vector fields to each other, but the structure that they form is something different. And as I said, the tangents at each point, if I collect all points, they form something called the tangent bundle rather than just the tangent space. So slight distinction between tangents at one point and the tangent vector field at a family of points. Can we get all possible abstract vectors at a point by combining tangent vectors linearly? Yes. In fact, any abstract vector at a point is a tangent vector. And I think I've explained it better in the book. But basically, if somebody gives you x equals ai dx d by dxi, where these are numbers, and says that this is a vector in this is a vector field in coordinates, written in coordinates on Euclidean space. Find me a curve for which at a given point these ai are the tangent vectors. It's very simple. I'll just declare that ai equals dxi by dt. In fact, I can even go further and say that xi is ait plus constant. Okay, just a straight line. So I'll take that straight line in my Euclidean space, and now I'll map the whole straight line back to my manifold. And I'll be assured that at the given point, the origin t equals 0, dxi by dt was ai, because obviously it's true of this curve, right? Dxi by dt is ai. So given any vector, it will be the tangent vector of some curve. So the idea that we started with a curve and then got vectors, we immediately realized that, but we could have started with any curve. And if you start with all curves through a point in a manifold, then it's intuitively clear that you will get all possible vectors in Euclidean space. So you really only need, let's say, to span Euclidean space, you only need n linearly independent vectors, and they form a basis. So the coordinates actually form a basis for the tangent space. Yeah. When we do calculus using spherical polar coordinates is different than doing calculus on S2, because in former case, no. Actually, Rajnil, so the point is this: three-dimensional space is always Euclidean, R3. Now that has three polar coordinates, r, theta, and phi. And that space is Euclidean no matter what. In r, theta, and phi, it doesn't look Euclidean. You may be fooled by the fact that something looks more complicated because you're just using different coordinates. Now you could say that the r, theta, phi is like one coordinate system for that point, and x1, x2, x3 is another coordinate system, and we know the map back and forth between them, right? So here we've not gone to S2 and we've not gone away from Euclidean space. Space is the same. R theta phi is one coordinate system, XYZ is another one. Now, because of spherical symmetry in physics, we often fix R. All the problem comes there. As soon as I fix R, I'm no longer R being the radial coordinate. Then I'm no longer in R3. Now I'm on S2, but S2 is a differentiable manifold and it's not Euclidean space anymore. Okay. So now I have the choice that on S2, I can use theta and phi, which completely cover S2 nicely. Although I have to be very careful about the origin, the range of theta and the range of phi, like minus pi to pi or minus pi by 2 to pi by 2 and so on. But I can also use three-dimensional Euclidean coordinates, always remembering that the sphere is embedded in that space. So x, y, z subject to x squared plus y squared plus z squared equals r squared. I can do it both ways. Okay, but you should be clear whether you are on S2 or R3. These are coordinate independent statements. So in both cases, when we use spherical polar coordinates, we are still in R3. It's only when we restrict that the value of radial coordinate is fixed that we go to S2. And it's of course convenient to do that because in the r theta phi coordinates, we lose one coordinate by doing that. But in x, y, z coordinates, we don't easily lose one because, right, it's just it's a space which is restricted by an equation in x, y, and z all three. Yeah. Could I elaborate on integral curves? Okay. So here's the concept of integral curve. It's actually simpler than it sounds. Here is R2. Somebody gives me at every point of R2 a vector. And he gives it to me in a, or she gives it to me in a continuous and differentiable way. You can sort of, now I'm being intuitive, so I won't stop to explain what exactly that means. But this, okay. Aditya gave a very nice example of a fluid flow. So there's a velocity vector. Physically, it should be a continuous and smooth differentiable, and it has this look. Okay, generically, it's a vector at every point. Okay, now take one point and follow it. Just in your fluid, take out one fluid particle and replace it with a red particle, which you can see as it moves. Just an idealized experiment. It's going to do something, right? That will move. And it will move in a continuous way such that all the tangent vectors that were given to us earlier are all tangents to the path of that point. That's the integral curve. In physics, it's fairly obvious. If I have a set of vectors, each of which is based at one point and tells me a direction of flow, then I can construct a curve such that that vector is the tangent vector of the given curve. Obviously, the tangent vector has to satisfy some smoothness condition, and that is embodied in this statement that the linear map x is from C infinity to C infinity function. So if it acts on a C infinity or differentiable function, it shouldn't take me outside that set. It should continue to be C infinity. Yeah, we are running quite late now. Yeah, field lines for electric and magnetic fields are integral curves. Yeah, I think we better end now. Set of all possible Jacobians between possible coordinates isn't always set of all possible. Aren't we always get orientable manifolds? Oh, Jacobians are not linear operators in the first place, huh, Tanmay? There's nothing linear about Jacobians. Jacobian is a determinant of del xi by del yj. That's not linear at all. No, no. Jacobian is quite a different thing. Jacobian is not related to a path on the manifold or to a function from the manifold to real numbers. Jacobian is literally related to change of coordinate system for the same point. Okay. So it's the derivative of the new coordinates, each one with respect to each of the old coordinates. That's all it is. If you want an example of Jacobian, we use a lot. In polar coordinates, we need to know del r by del x, del r by del y, del r by del z, then del theta by del x, del theta by del y, del theta by del z, and then similarly for phi. So there are 9 derivatives. I arrange them in a 3 by 3 matrix and take the determinant. That's the Jacobian. That's just one example, but in general, any change of variables will have a Jacobian determinant, and that's not at all anything linear, and it's not related to tangent vectors in any way. Yeah, good. Thank you very much.